For this lab, I headed down to the Tech Recreation Center. I wanted to understand the physics of what is occurring when objects move at a constant velocity. Tech Rec's billiard tables were a perfect place for experimentation. In pool, when a ball is struck, a force is applied and the ball accelerates as stated according to Newton's second law. However, when the strike ends, the pool ball will theoretically remain at a constant velocity since no net force acts on the ball. We made a computer model based on that assumption. However, due to unforeseen forces acting on our ball, our model was imperfect. But more on that later. First, let's break down the physics. Here is Newton's second law, a restructured version of the classic F equals ma equation. Newton's second law tells us how forces cause a change in velocity. Now after the ball is hit and it stops accelerating, forces still act on the ball, namely the gravitational force, the force due to gravitational attraction, and the normal force, the force of the table pushing back up. But these forces cancel out to equal a net force of 0. Thus, the equation simplifies so that the initial velocity is equal to the final velocity. This is why our pool ball should remain at a constant velocity. Let's get empirical evidence to support our assertions. Bringing back a clip from before of a pool strike, we can analyze the object's motion with a program called Tracker. Tracker takes in changes on an arbitrary coordinate axis, shown in purple, with the origin placed at the position of the first ball. In my video, the ball traverses approximately in the direction of the positive x-axis. What if I had flipped my axis with y or z? Then the change would have been in that component direction and I would have simply had to do calculations with that component instead. However, the magnitude of the velocity and position would remain the same. Our tracker data can then be used to build a computational model of what the motion future would look like. We simply have to plug in information for parameters found in our video, including the mass of the ball, its initial velocity found with the rate of change over the first two frames, the initial position, which we assigned as the origin, and the force, which we assume to be 0. Then, our model, which contains Newton's second law equation built in, simply iterates over a specified time interval, updating the velocity and position as it goes along. It simply uses the physics equations explained before to build our model. Here is a video representation of what our model looks like. So how did our model fare against the data? In this graph, the line represents our model and the dots the actual observed values. Overall, our model correlates fairly well with an r-squared value of approximately 1 and a slope or velocity of 1.55 meters per second. It fits especially well at the beginning of the observation period. However, towards the end of the time interval, it becomes less and less accurate. Graphing the residuals, or the expected minus the observed for each point, confirms this result, the residuals showing a definite increasing difference. Why the discrepancy? It is most likely attributable to the frictional force, a force that acts against the motion of the ball. Since this is an imperfect world, some of the kinetic energy of the ball is transferred away as heat and sound. More simply, a force is indeed acting on the ball after it is hit, resulting in a change in velocity. All in all, my model was an imperfect representation of the data. My model would be more accurate in the depths of space where no frictional drag force is acting on the ball.